क्या है?
अब शुरू हुआ है।
ओके। You can do that even at the end a little bit. Okay. So once again, good morning to everybody and Suprabhat. And Radhe. Good. I love that Radhe. Very pleasant. Okay. So let us spend a couple of minutes trying to recap what we have been doing in the last few days. Professor Garima Punetha has been working very hard in the organization of this event called the Workshop on Quantum Mechanics. It's a very thoughtful title that she has given, and we all, on our part, are trying to do some justice to that topic, to that title, to that theme chosen by Professor Garima Punetha. Of course, and we are very grateful to her. We are very grateful to all the audience, all the students, that we are here at such a beautiful, lovely place at the LSM campus of the Pithoragarh campus of the Almora University, right? Yes. Very good. So, you see, we had a brief introduction on quantum mechanics. Then, we had a further good introduction on the birth of modern quantum mechanics and the concepts involved in the modern quantum mechanics. And if and when you happen to learn things further, and if and when I also happen to teach you and the similar people somewhere in some form, for me, these concepts are very crucial, very important, because they, although from you who could be easily here next week, Dr. Garima would be organizing some event, and I hope we have some further conversation, possibility of talk or conversation on this topic, when I would tell you the frontiers going beyond what we learn in this particular event. So there is a concept of fermionic variables. Fermionic variables are anti-commuting variables. They also do not have any classical analog, like the way you have for commutation, commuting variables and commutation relations. Right when you come at the first, second, third, 8th, 9th, 10th, 11th level in your early school, even without being told, you always deal with bosonic variables. So if you write x plus y whole square, but you write x square plus y square plus 2xy usually, without bothering that you probably should write x square plus y square plus xy plus yx. Okay? Without knowing that these x and y are commuting variables. So xy is equal to yx. If x and y were fermionic variables, this result might not hold true. Okay, because fermionic variables, when they switch their places, they pick up a minus sign. That is the difference. Very good. So this is what I would tell its importance in the context of quantum mechanics. Okay, which also hold, you see, most of the concepts that you develop in quantum mechanics, when you generalize your considerations, where you go beyond the dependence on t for your variables like q's and p's, when you also treat them that they also depend on x, y, z and t. So which I call as x mu. X mu is a variable or some quantity which depends on x, y, z and t. Okay. So that means by putting x mu, we start talking in terms of a Minkowski space. Okay, where mu can take the value 0, 1, 2, 3. 1, 2, 3 correspond to the space variables, and x0 is really time variable, which is c into t. Okay, very good. So let us then first take up a few things, and initially I would be talking on the one-dimensional harmonic oscillator. Okay, and for this I would be using only commuting variables. But then after I am through with that concept, I would tell you what happens if I had fermionic variables. That I would spend only a couple of minutes, but tell you some important results, like in my simple conversation, anti-commuting or anti-symmetric property of a wave function would come out without any efforts, and Pauli-exclusion principle would also follow without any extra efforts. Okay, so in that context, because then once you generalize your quantum mechanics to so-called quantum theory, where instead of qi, pi, you have some variables denoted by phi of x mu and pi of x mu, which play the same role like coordinates and momentum. But they are for fields, so they depend on x mu, x, y, z, and t. And we knew without being told, when you do mechanics or classical mechanics, you talk about an n-dimensional Euclidean space, where you have q1, q2, q3, qn, or x, y, z, and px, vy, pz, and so on. They all depended only on time, and that was mechanics. When we have too many of q's and p's, or when we have, then we better talk in terms of a generalized system of coordinates. They are called generalized coordinates, and we denote them by qi and pi. So they are generalized coordinates. Then we define canonical momentum, which is partial derivative of a Lagrangian with respect to the velocity. And Lagrangian is always the difference of the kinetic energy and the potential energy, whether it is mechanics or a field theory. All right? Then in quantum mechanics, I will talk the simple case of a one-dimensional harmonic oscillator, where I will have only one x and one px. Okay? It can be easily generalized to a vector r or something. You can generalize it to more variables, okay, or in 3 dimensions, x, y, z. So this is one thing. But this, you see, why I have chosen this topic, because of the limitation of time, I had to be choosy for what should be ignored, what could be taken, and I prefer to keep this topic for our proper consideration, because it's the results obtained here have a far more reaching consequence, because they are very, very useful. Okay? So now again, as per my characteristic, I always like to start with the simple thing. So 1/2 mx dot square minus 1/2, let me say, kx square. This potential kx square, if you plot it, this would be a parabola like that. So parabola is y square equal to 4ax, you know, or x square equal to 4by or 4ay. So one of them is quadratic, one of them is linear. So this is also called as a parabolic potential. Okay? So whenever you have a parabolic potential, it's a harmonic oscillator. And here it is. Now, from here, you define Px, h, and x dot, or before that, let me put del L over del x dot, which is n x dot. This then should be used to obtain x dot equal to Px by n, and then you use the Legendre transformation to define h, x dot minus L. This is the standard procedure of so-called Hamiltonian formulation.